Welcome. In this video, we're going to remind ourselves of what the derivative as a function is actually telling us. And then we're going to use a GeoGebra demo, which is in Canvas, to make a guess as to what the derivative of e to the x is. So if you recall, the derivative of a function, dy dx, of a function, y equals f of x, tells us the instantaneous rate of change at any point x. We can also say it tells us the slope of a tangent line at any point x. So here it is written down and reiterated. So the first derivative tells us the slope of the line tangent to this function at any point x equals a. And we can also rephrase this as this tells us, that is this value here, tells us the instantaneous rate of change at any point. And these are equivalent statements. Okay, so now let's use this answer and the GeoGebra demo to make a guess as to what the derivative of y equals e to the x might be. So here is the demo from Canvas, or you might be looking at this online. And then the important values of this demo are down here. So the slope of the line tangent and the value of e to the x. Up here, I just gave you some approximations of e raised to some powers, since when you move the slider around, you notice that at this point, it's e raised to the 1 power, and that way you know it's just e raised to the 1 power is about 2.72. So that's just there to help you read kind of these graphs and what's going on here. Now the red line is tangent to y equals e to the x at whatever point x equals a we're at. Right now, a is equal to 0. So when x is equal to 0, y, that is the output of f of x equals e to the x, is equal to just 1. And then what is the slope of the tangent line here? Well, if you notice, this point goes through -1, 0, and 0, 1. So it looks like this slope is just 1 over 1. And when you work this out using dividing the change in vertical values by the change in horizontal values, you end up getting 1. And that's here. Okay, so what about, let's say, -1? Well, the output of this function, e to the x, is 0.37. And the slope, that is the derivative of this function at -1, is also 0.37. So that's also fairly cool, because again, 0.37 is just an approximation of e to the -1 power. So what I'm seeing here is that the instantaneous rate of change of this curve, y equals e to the x, at this point is the same thing as its output value at this point. And if you go through, you'll notice that is the case for every single point. If we let x equal 1, we have e to the 1 power, which is just e, or about 2.72, and the slope of this tangent line, that is the instantaneous rate of change at x equals 1, is also 2.72. So it's also e. Let's take a look at e squared. So that is at x equals 2, we have e squared, and that's approximately 7.39. And the instantaneous rate of change of e at the line y equals e to the x at x equals 2 is also 7.39. So from this demo, we're able to see that no matter where we move our point to our x value, the instantaneous rate of change will always equal the output value of e to the x. Okay, so from the demo, we figured out that the derivative, that is a y prime of this function at x equals 1, so the derivative is just e. And we also figured out that the derivative of e to the x, say at x equals 2, is just e squared. So that's the really cool thing about the number e, is that the value, that is the output of this function, is the same as the slope of its tangent line at that x value. So the derivative of e to the x is just e to the x. So to reiterate, the really cool thing about the natural exponential function is that its instantaneous rate of change anywhere is the same as its output at that same point. I hope you can find the beauty in that fact. I hope you found this video helpful.